Hello and thank you for watching my video. My name is Astrid Krasniqi. I'm CCNA and CCNP certified instructor. On this video we are going to cover CCNA semester 3 Scaling Networks, and this is chapter 6 Multi-Area OSPF. Chapter 6 is divided in two sections. We have section 6.1 Multi-Area OSPF and section 6.2 Configuring Multi-Area OSPF. This is section 6.1 Multi-Area OSPF Operation. Upon completion of this section, you should be able to explain why multi-area OSPF is used and explain how multi-area OSPF uses link state advertisement or LSAs in order to maintain routing tables. Explain how OSPF established neighbor adjacency in multi-area OSPF implementation. In a single area OSPF, all routers are in area 0. Area 0, if you remember, it was called a backbone area. Now, single area OSPF is useful in a small network with only a few routers. Issues that we have with a large OSPF or large single area OSPF would be like large routing table. OSPF does not automatically summarize routes, and therefore routing table can become very large depending on the size of the network. Now you remember the OSPF you cannot summarize because it's a link state protocol. That means that every router has to have a synchronized database, so we can't summarize anywhere. For example, one of these small routers here in the corner says, oh, my routing table is too big and I'm running low on memory. So the first problem with a single area OSPF, large single area OSPF, would be that you have all the routers are building a large routing table because we can't summarize. Second problem would be large link state database, LSDB. The LSDB maintains an entry for every network in the area, even if not every route is selected for the routing table. Too many routes in the one area would make the LSDB very large and increase the load on the CPU. For example, because they have to have a synchronized database. For example, a router down here needs to have about every network there are in these routers, even though, or this router for example, even though the path will be towards towards router 1. So even selecting one path, but he has to keep or maintain every network that these routers down here are advertising. I'm receiving too many LSAs. The third issue would be frequent SPF algorithm calculations. In a large network, changes are inevitable, so the routers spend many CPU cycles recalculating the shortest path algorithm and updating the routing table. For example, again, let's pick this router down here. If there's a change here, this router has to go through the algorithm again and run the algorithm, if link goes up or down here, even though the path always going to go towards router 1. So you want to protect, or you want to save the CPU cycles of these routers from all the changes that are happening here. So just to remember, there was three problems. First problem, there was a routing table was getting too large in a single OSPF or large single OSPF area because we couldn't summarize anywhere. Number two, the problem was like too many LSAs flying around in the network. Third problem is the frequent shortest path first algorithm is being calculated on every router. So my shortest path first algorithm is running too often for me to route properly. Multi-area OSPF. Multi-area OSPF uses a two-layer hierarchy using a backbone area that interconnects regular areas. So we have a backbone area that is going to interconnect all other regular areas. Useful in large network deployment to reduce the processing and memory overhead. All regular area must interconnect to the backbone area or area 0. You have to remember that every area must have direct connection to the backbone area. Interconnecting routers are also called an area border router. So now we have divided into small areas. We have area 0, which is our backbone area. Another name for this would be a transit area, because we don't connect the PCs on that area. It's only going to transit, like for example, end device data to another end device data to this side. So this area, backbone, transit area, whatever you want to call it, but we don't want to connect any end devices to that. The routers that will connect our areas together are called area border routers. These routers, they keep two databases, one for area 0 and another database for area 1. So they will keep synchronize two databases. So obviously we want to put more powerful routers as our area border routers. See, backbone area or transit area. OSPF area, whose primary function is the fast and efficient movement of IP packets. Backbone area interconnects with other OSPF area types. Generally, end users are not found within a backbone area because this functions as a transit area. Now, one area cannot talk to another area without going through the backbone area. Even if there's a link, for example, here within two areas, they can't communicate with each other because it's like a loop prevention in OSPF. So we have to go through the area 0 to get to the other destination or other area. The backbone area is also called OSPF area 0. Hierarchical networking defines area 0 as a core to which all other areas have a directly connected or are directly connected. Other areas are called regular area or normal areas. Connects users and resources. So here we are connecting users and resources. Areas are usually set up along functional or geographical groupings. By default, all traffic from other areas must cross a transit area. So from all regular areas or normal areas, they can't talk to directly. They have to go through area 0 or our transit area. A regular area does not allow traffic from another area to use its links to reach other areas. So for example, let me mark it here. If we have it like this, yeah. So if we, for example, have connection here like that, traffic still can't go from this area to this area. They can't use this link because it has to go through area 0. It's a loop prevention mechanism for OSPF. These are the advantages of multi-area OSPF. So first, we have a smaller routing table, few routing tables entries because network addresses can be summarized between areas. So route summarization is not enabled by default. So here, because router 1, for example, is keeping like a synchronized database from both areas, area 1 and area 0, can take all these routes from area 1 and synchronize them and summarize them, send them to area 0 as only one route, only one. So here, area 1 is reducing the routing table because they are being summarized. Only place we can summarize is at the area border router. So router 1 can summarize and router 2 can summarize. Reduce link state updates overhead. Minimize the processing and memory requirements. So when there's, for example, an update here or LSA or something, router 1 will not advertise that LSA to other areas. And reduce frequency of shortest path algorithm calculations. Localizes the impact of topology change within an area. For instance, it minimizes routing update impact because the LSA flooding stops at the area boundary. So topology change impacts local area only. The area border router, router 2 in this case, will isolate the area 51 only. Link failure affects the local area only. Routers in area 0 and 1, they don't need to run the shortest path first algorithm. Cisco OSPF implementation guidelines. Now these are the guidelines from the Cisco when you implement OSPF. The optimal number of routers per area varies based on the factors such as network stability. However, these are the Cisco guidelines. They recommend that a router should not be in more than 3 areas. So you don't want to connect one router to more than 3 areas because it's going to need to keep synchronized database for each area. And obviously it's going to, you might run out of resources. An area should have no more than 50 routers, right? As soon as you become 50 routers in one area, start splitting them. Any single router should not have more than 60 neighbors, right? So here we can see like how big kind of topology the Cisco is thinking about. You're going to have 60 neighbors, one router. Internal routers, you need to know that this is the router that has all of its interfaces in the same area. So all the routers, all the interfaces, if they are within one area, it's called internal router. So for example, all these 4 routers all the interfaces are in area 1. So that's the internal router. In area 0, these 2 routers, all the interfaces are within area 0. So they are called internal routers. And as well as Area 51, we have 4 routers here. Backbone router, it's called any router that has a single, at least one interface connected to Area 0. So if you have one interface connected to Area 0, then you're called a backbone router. Now in OSPF, you're going to have more than one name. So these 2 routers, for example, down here, they were called internal routers. Now there are backbone routers as well. So internal backbone routers. Area border router. This is the router that has an interface attached to multiple areas. The area border router maintains a separate link state database for each area that it's connected to. This is the exit point for the area. Distribute the routing information into the backbone, and the backbone routers then forward the information to other areas. So here, in this case, we have router 1 and router 2 are our area border routers. Now we have another type of router. So we have autonomous system boundary router, ASBR. This is a router that has at least one interface attached to an external non-OSPF network. An ASBR can redistribute non-OSPF networks information into and out of the OSPF network. So for example, here we have this is our OSPF process. So here is our autonomous system for OSPF. If one router is connected to another autonomous system, for example, RIP, EIGRP, or even if it's redistributed static routes, right? The static route towards a default static route towards the internet, that router becomes the ASBR. Now you can see router 1's got 3 names. I can say router 1 is ASBR, which is true because it's got connection to another autonomous system. Router 1 is ABR because it's got connection to Area 1 and Area 0. As well as router 1 is a backbone router because it's got a single connection to the backbone area. So multi-area OSPF, for example, here we can choose what are the routers, what are the router types. So if you stop the video now and try and figure out which routes are in multi-area OSPF routers, which ones are normal area, what type of routers are there, and so on. So the Area 0 is a backbone area, Area 1 is a normal area, and Area 51 is a normal area. Now the router 222 is autonomous system boundary router because it's got a connection to the ISP here. So that's an ASBR. Router 1 here and router 3 is ABR, so all with a router ID 111 and 333 are ABR because they got a connection to the Area 0 as well as Area 1. And then these are internal routers. Down there you see 33, 22, 100 and 200. OSPF link state advertisement or LSAs. Multi-area OSPF LSA operation. Now link state advertisement, LSAs, these are the packets that go inside, these are the information that goes inside link state update, yeah? So you remember from the packet types, link state update was full of LSAs. LSA states, LSA's information about the state of the router's link. This information includes, what do we send? We send IP address of our link state. We send the type of the network. We send cost. How much does it cost us to get to that network? And do we have any neighbors on that link? So first, for example, if router 1 is sending an LSA here. So the router 1 is saying, okay, well the network address is 10.100/16. My IP address on that network, on the interface. What type of network is it? Okay, well, it's Ethernet. What's the cost to get for me to get to that network? So you tell the neighbors, so they can add their cost. And then how many neighbors do I have there? Oh, I have nothing because it's Ethernet, so there's no neighbors on this interface. OSPF LSA types. Remember we had 5 different packet types in OSPF. First packet type was hello. This packet was to establish and maintain our adjacency relationship with the neighbors. So we establish our neighbors and we maintain them by sending hellos. In the fast link, if you remember, we send every 10 seconds, and slow link, we send them every 30 seconds. Then second packet type, after we establish our neighbors, then we start exchanging our database, what you know and what I know. So that is database description packet, describes the content of the OSPF route link state database. Routers link state database. So we only describe in the content, okay? So in OSPF the routers, they don't exchange everything in the database. They just exchange like an index saying, okay, well, I know about place network A, B, and C. And the other neighbor will look and say, okay, well, I already know about network A and B, so that's it. I don't know about network C. So what they do, they send a packet type 3, which is link state request, saying, okay, I didn't know about network that you know about network C. Can you tell me a bit more information? So that is for packet type number 4, which is okay, well, here is a link state update. Now, instead of just sending index about network C, I'm sending everything that I know about network C, including what do we have, the network ID, our IP address, the cost, and what type of network is it, and how much does it, do I have any neighbors on that network? And the fifth packet type was link state acknowledgement. Now, in the fourth packet type, or link state update, these are the LSAs inside there. So there's quite a few LSAs, but for us, we only need to know the first 5. So we need to know LSA type 1, which is a router link entry record. Is code that gets O in a routing table. So this is generated by each router for each area it belongs to. It describes the state of the router's link to that area. These are only flooded within a particular area. These links, so they're not sent to another area, so they confine within area. This is the status, and the costs are 2 of the description provided. Then we have LSA type 2. These are network link entries, and in the routing table they get code just O. These are generated by DR, designated routers. These are only available in multi-access networks. They describe the set of routers attached to a particular network. LSA type 2 messages are flooded again, same LSA type 1 and 2, within area. So they don't go from one area to another area. Then we have LSA type 3. These are summary link entries, and they get a code IA on the routing table. These are originated by area border routers. They describe the link between the area border router and the internal routers of a local area. These entries are flooded through the backbone area to other ABRs. Type 3 messages describe routes to the network within the local area and are sent to the backbone area. Type 4 messages describe the reachability of ASBR. These links entries are not flooded through the totally stubby areas. Okay, first of all, let's talk about type 3. Type 3, remember, ABR, for example, is connected to area 1, which is normal area, and area 0, which is a backbone area. It will take all the routes they knows in the normal area, type 1 routes they knows from within that area, and it will summarize them. It will send them as a type 3 route to the backbone area. So other areas that will know about those routes. It's because type 1, we are not allowed to send them. You're going to see on the slide coming up as well. So, and type 5, and then I'll come back to type 4. Type 5, external routes. And these are generated by ASBR. They're saying, okay, well, I got an external route I'm learning from the EIGRP. I need to bring it to my OSPF, and I'll send them as a type 5. But the thing is that the information inside there, it doesn't change. It just says, okay, well, to get to the EIGRP network, go to the ASBR. Now, area border router, they do send information how to get to the ASBR with the type 4. Okay, as soon we're gonna see them in a bit more depth right now. So for example, router LSA type 1, router links LSA, these are generated by every router within the area. So generated by each router for each area they belongs to. Describes the state of the link in the area to which the router belongs. These again, remember, they are flooded within the area on multi-access network sent to the DR. Denoted by just an O in the routing table, or C if the network is directly connected. Area border router will include a set of LSAs for type 1 for each area they belongs to. When a new LSA type 1 is received and installed in link state database, the router forwards the LSA using hop-by-hop or asynchronous flooding. So for example, each router will flood type 1 LSA within area. So we have type 1 in this area, area 1, but they don't go to the other areas, so they are within this area. So area 0's LSA is in blue here, and then in purple LSA type. And then in area 51 we have LSA type 1s here as well. So they have all LSA type 1s, they are within area, they stay here. So area, they don't go outside. As well as type 2. LSA only announced a link network within the area. router received LSA type 1 from neighbor floods this LSA type 1 to other neighbors within the same area. So when we see show IP route, we will see LSA type 1, let's just see O there, as we learned it from within our area. LSA type 2, these are the DR, announcing themselves, okay, I'm the DR, I'm a designated router on this network. So they are, again, they're flooded only within the originating areas. LSA type 2 are in the link state database for all routers within the area, even those routes are not on the multi-access networks or DR or other multi-access networks in the same area. Area border router might include a set of LSA type 2 for each area it belongs to. So for example, if you stop the video again and have a look at this, where do you think the LSA type 2 would be generated? Well, LSA type 2 will be generated on multi-access network, and this network here is a point-to-point. This one here is point-to-point, point-to-point, so not in area 0. But in area 1 we have LSA type 2, because here we have a multi-access network. And on this multi-access network we need to elect one DR, designated router, where we're going to send the updates to that DR. For example, say that this is our DR, designated router. All updates, they're going to go to DR. So this DR will announce saying, okay, well, I'm the designated router here. This is type 2 LSA here. Now in this network here as well, like between them two, it's a crossover cable here, we need to elect the DR. Now one of the statements there was saying that it will be within area. So you will see a type 2, for example, on this router, even though this router has got nothing to do with the multi-access network, not on this side and not on this side either. But you will see on the database, you will see the type 2 from here. LSA type 2 flooded within area by designated router. LSA type 3, these are summary netlink states. LSA type 3 summary LSAs, these are originated by area border router. They do describe the links between the area border router and internal routers of the local area. Area border router will include a set of LSA type 3 for each area they belong to. LSA type 3, they are flooded through the backbone area and to other ABRs. Routes learned via LSA type 3 are denoted with the IA or inter area in the routing table. So for example, this router, what it's going to do is going to take all LSAs from type 1 here, all type 1 LSAs, and it send them as a type 3 LSA here on this side. It can summarize. By default it doesn't summarize, but you can summarize there. So you can, instead of sending 3 or whatever networks you find here, instead of sending them that many, you can summarize them into 1. So only area border router and ASBR can summarize. When we do show IP route, we're gonna see it on the routing table as a OIA, so inter area. LSA type 4 ASBR summary LSAs, these are originated by area border router. They are flooded throughout the area, describes the reachability, how to get to the ASBR. How do we get to the ASBR? Advertises an ASBR router ID, not a network. Included in the routing table is IA route. So for example, here we have a router 2 is sending LSA 1 EBIT. So EBIT is set saying that I've got access to the external network. But now when that route gets, for example, to this router down here, this router down here doesn't know how to get to, because it doesn't change the update. So this router doesn't really know how to get to this ASBR. But LSA type 4 generated by the area border router says, okay, well, if you do want to get to that router, this is how. So it tells how to get to the network or to that router. It's not a network, it's a router. It's ASBR path. OSPF LSA type 5, these are external links. So if you bring a network from outside, like EIGRP or static route, then they are going to be generated by ASBR. Now, ASBR, they're going to send type 5. This type 5, you see, doesn't get changed. From the source, from the ASBR to the destination of this area, for example, they always say as a type 5. So it tells you how, okay, if you want to go to that network, send it to this router. Now this router might got no idea where is this router, but the area border router has sent type 4 how to get there. Now it's not sent to a stop network or totally stop networks. These two types of networks you're going to learn if you're studying CCNP. You're going to be more, we're going to talk about them. But it just tells what type of LSAs are allowed. For example, in a stop network, the only LSA type 1, 2, and 3 are allowed, but not 4 and 5. In totally stop network, is only 1 and 2 are allowed, but not 3, 4, or 5. So for example, when you create type 5 LSA is when you redistribute a route. You create a static route and you redistribute it into OSPF, then that router becomes a ASBR. So redistribute commands creates an ASBR router, LSA type 5, it's originated by ASBR. Description destination describes the destination network external to OSPF routing domain, and is flooded throughout the OSPF autonomous system except to the stop and totally stop areas. OSPF LSA type 5, that could be E1 or E2. External router falls under two categories: external type 1 or external type 2, which is the default. Now the difference between the two is the way the cost metric of the route is being calculated. The cost of type 2 route is always the external cost irrespective of the interior cost to reach that route. A type 1 cost is the addition of the external cost and the internal cost used to reach that route. A type 1 route is always preferred over type 2 routes for the same destination. For example, type 2 is the default here. If this is our ASBR here, down here, and it says, okay, well, this here, that's our ASBR. It says to get this network, the cost, imagine the cost is 5, the ASBR saying. To get to the external network, the cost is 5. Now type 1, it doesn't get changed. From the source to destination, so this router here says, okay, well, to get to the external network, it's 5. Okay, what do I need to calculate how to get there? To add from 5 plus whatever the cost is here, whatever the cost is here, and so on. Continue adding it. Just whatever the ASBR says, that's all I take as a cost. Type 1 external router would be like, for example, if you have 2, say here and here. Now the network is same, this one and this one is the same advertised from both of the ASBR. Now this router has to choose, do I want to take this path to destination, or do I want to take this path to destination? So now I need to add which one is faster, where do I get faster? Do I get to this ASBR faster or to this ASBR faster? OSPF routing table. Now when we see show IP route, we see some OSPF routes, and we see some of them, they have just code O. So if you remember, these are just within the areas. So if we learned a network that is in our area, intra area, type 1 or type 2 LSAs, then we get code O. If we see the code OIA, it means that we have got a network, a summarized network from another area we learned. So this network is not in our area. It's been advertised as ABR, area border router, as type 3. And we can see a network OE1 or OE2. These are external LSA describing a non-OSPF network. Steps to OSPF convergence, for example, first calculate the intra-area OSPF routes, then we calculate the best path to the inter-area routes, and then we calculate the best path to the external non-OSPF networks. Similar we will have in IP version 6, show IPv6 route, for example, we see O inter-area, then OIA or OI or inter-area, and OE2 for external routes. Thank you very much for watching my video 6.1 multi-area OSPF. Please have a look at other videos and don't forget to subscribe. Next video 6.2 configuring multi-area OSPF. This has been Astrid Krasniqi. Bye bye.